Welcome to Echoes of My Imagination. My name is Tracy Lee. Sit back, relax. Let me tell you a story. Today's story is part 9 of How the World Works. Let's get into it. Extremophiles. I am life where survival seems impossible. For a long time, humans believed life required gentle conditions. Moderate temperatures, fresh water, sunlight, and breathable air appeared essential. Deserts, deep oceans, acidic lakes, and frozen ice seemed too hostile to support living systems. But life proved far more adaptable. Across the earth, organisms exist in environments once thought completely uninhabitable. They thrive in boiling water, within solid rock, inside concentrated acids, and beneath pressures strong enough to crush steel. These organisms are called extremophiles. They are not unusual because they live in difficult places. They are remarkable because they have evolved biological systems that function under conditions that destroy most other life. I exist wherever life pushes against the limits of chemistry and physics. Temperature defines one of those limits. Most organisms function best within a narrow range of heat. Proteins, which carry out nearly every chemical reaction in cells, depend on precise shapes to operate. Too much heat causes those structures to unfold, stopping the reactions that sustain life. Yet some organisms thrive where water approaches its boiling point. These organisms are called thermophiles. They inhabit hot springs, volcanic soils, and hydrothermal vents deep in the ocean floor. Their enzymes remain stable at temperatures that would quickly destroy ordinary proteins. Special molecular bonds strengthen their structures, preventing them from unfolding under intense heat. Even more remarkable are hyperthermophiles. These organisms live in environments above 80 degrees Celsius and sometimes near 120 degrees Celsius. In the dark waters surrounding hydrothermal vents, they grow in fluids heated by magma beneath the seafloor. In these places, sunlight never reaches, yet life continues through chemical energy. At the opposite extreme, life persists in intense cold. Psychrophiles inhabit glaciers, polar oceans, and permanently frozen soils called permafrost. Their cellular membranes remain flexible at low temperatures, allowing nutrients and waste to move across them. Their enzymes operate efficiently, even when chemical reactions normally slow in the cold. In these frozen environments, microbes can remain active within thin films of liquid water that exist between ice crystals. Life also survives where pressure becomes immense. In the deepest parts of the ocean, miles below the surface, pressure increases with every meter of depth. At the bottom of trenches such as the Marianas Trench, pressures exceed 1,000 times the atmospheric pressure at sea level. Organisms adapted to these conditions are called piezophiles, sometimes known as barophiles. Their cell structures remain stable even when compressed by enormous weight. Membranes, proteins, and enzymes function normally under pressures that would collapse most biological systems. Chemical extremes also support specialized life. In some environments, water contains high concentrations of acids. Acidic lakes, volcanic pools, and mineral drainage from rocks can produce conditions where the pH drops to levels comparable to strong industrial acids. Organisms adapted to these environments are known as acidophiles. Their cell membranes prevent acid from entering the cell interior, while internal chemistry maintains a stable pH that allows enzymes to function. Other environments reach the opposite extreme. High alkaline lakes such as Lake Natron and certain soda lakes contain large amounts of dissolved salts and minerals that raise the pH far above neutral. Organisms called achillophiles thrive in these conditions, maintaining internal chemistry that remains stable even while surrounded by highly basic water. Salt itself creates another powerful environmental challenge. When water contains extremely high salt concentrations, it draws water out of cells through osmosis, dehydrating most organisms. Yet halophiles survive in places such as salt flats, evaporating lakes, and salt mines. Their cells contain specialized molecules that balance the salt concentration between the interior of the cell and the surrounding environment. This balance prevents dehydration and allows normal biological activity. High-energy radiation can break DNA molecules and damage cellular structures. However, certain organisms, such as the bacterium Deinococcus radiodurans, possesses extraordinary repair systems. When their DNA becomes fragmented by radiation, these organisms rebuild the damaged strands piece by piece, restoring their genetic information. Other organisms survive with almost no water. Xerophiles inhabit deserts and extremely dry environments where liquid water may be absent for long periods. They protect their cellular machinery by producing molecules that stabilize proteins and membranes during dehydration. When water finally returns, these organisms quickly resume normal metabolic activity. Some microbes even live deep underground. Within cracks in rocks kilometers below the surface, microorganisms survive without sunlight, relying instead on chemical reactions involving minerals in the surrounding rock. These endoliths obtain energy from chemical gradients produced by geological processes. Their environment remains dark, isolated, and slow-changing for millions of years. Extremophiles demonstrate that life is not limited to comfortable environments. Instead, life adapts by modifying the chemistry of cells, the structure of proteins, and the stability of genetic material. These adaptations reveal the remarkable flexibility of biological systems, where heat, pressure, acidity, salt, cold, dryness, or radiation push against the limits of survival, and some form of life often emerges that can withstand those forces. The study of extremophiles also reshapes how scientists think about life beyond Earth. If organisms can survive in boiling vents beneath the ocean or inside Antarctic ice, then environments on other planets or moons may also support life. Subsurface oceans on icy moons, ancient lakes on Mars, and other extreme environments throughout the solar system may not be as lifeless as once assumed. Extremophiles show that life does not simply endure the conditions of a planet. Life learns to inhabit them. I am life at the edge of possibility. I am Extremophiles. And that's it for today. Thank you for joining me for Echoes of My Imagination. My name is Tracy Lee. Don't forget to subscribe, share, like, and follow, and I'll catch you next time.